Okay, so welcome back. So our next speaker is Professor Siddhartha Sharkar from ISR Bhopal. Now, as a matter of fact, Professor Sarkar is the first PhD student of Professor Ravi Kulkarni after he returns back to India. So, Siddharth, over to you.
Okay. Yeah. Am I audible now? Yeah. Okay. So I think I'm visible, but I can't see the screen. It looks very different. It's a pleasure speaking in this conference, and many of the relevant topics I'll be talking about, which came up from one of the famous work of Ravi Kulkarni. So it's indeed a pleasure talking in his 80th birthday, and I'm happy to be here. So let me just start with sharing the screen now. Okay, is this visible? Am I audible to everyone? Okay, so I can switch the place. Okay, so there was a slight typo in the title I gave earlier, so it should be finite groups of symmetries of surfaces. So let me go back to where it all started. So I'll be introducing few notations. We take n sub k to be the set of all integers, which is at least k. And k could be any arbitrary integer as well, doesn't matter. And this notation, sigma little g, would always denote a closed compact orientable surface of genus G. Okay, and then for a finite group G, I'll be calling a group acts, this group G acts on this sigma G, so which I'll denote by this notation, if it acts via orientation preserving homeomorphisms. Okay, so these are pretty standard. I always will be having a finite group, and this is a little surface over here. This is closed compact orientable and of genus G. Like for G equal to 0, it's sphere. G equal to 1, it's torus, and for arbitrary G, it's the join of the G many torus together. Okay, so one of the results of Nielsen was as progressed as follows. So you look at the Teichmüller space of sigma G, which basically is the collection of all complex manifolds, which are parameterized and marked at certain points where the actions could be visible as fixed points. So this is why it's called marked points. And you look at it modulo the isotopy, meaning that two complex manifolds, if they are isotopic, I'll ignore them. Okay, so under this quotient, this become complex manifold again of dimension 6G minus 6, that is kind of very standard. And then there is another group which is called mod, the mapping class group, which is denoted as mod sigma G over here. So this is the orientation preserving group of all orientation preserving homeomorphisms on this sigma G modulo its identity component. Okay, so if you look at this, ignore this quotienting. So if you're this homeo plus sigma G definitely acts on the complex manifolds, preserves this. And there are some simple exercises proving that, okay, so this action would respect this isotopies. So then the action goes to the Teichmüller space, and then the identity components also do something trivial. So I'll have this action. which is called natural action. So one of the famous theorem of Nielsen, it's called mutual realization. It's basically says if I look at a finite subgroup of this mapping class, then the fixed points under this natural action should be non-empty. And one of the consequence, this is where we actually start, is that the finite subgroups of the mapping class is basically same as the finite groups which acts on sigma g. So this I'll be denoting as the finite. So this little less than little infinity means these are finite. This is the category of groups, and this basically means the ones which are acting on sigma g. Okay, so this means basically the question of classifying finite subgroups of mapping class, which is geometrically very important, is essentially the same as look at the questions of finding out all finite groups which act on sigma g for a fixed genus G over here. And this question was kind of well known. I mean, probably 100 years by now or 150 years that genus G and 1, these groups are all well listed and basically everybody knows it. But the problem started when people started looking at the genus greater than equal to 2. It is difficult to compute because the very good reason that there is no inductive process. Let's say if you ended up computing finite groups for G equal to 2, for G equal to 3, your earlier computations won't help. Okay, but still there was, I think, some attempt by these two authors over there. I don't remember the years. Kuribayashi and a separate paper by Wooten. They probably one paper covered until genus 4, and then there was a desperate attempt to cover up all possible groups or list all possible groups of genus 5. And at that point, people realized that, okay, so this is kind of a very big challenge. Like from 6 onwards, I might require several pages. And if I reach genus 12, you need machines to kind of list down what are the possible groups. So at that point, this is a question which is on the reverse direction. So you should look at probably fix a group and look at all genus where the group can possibly act. Okay. And there is this little result which is also called Hurwitz bound. So due to this, it just says that I don't have to go too far. So if I fix a group G, so all the groups okay, so all the groups that happens to be here are bounded above by this number. Now the point is, this has an advantage if you look at over here also. So the spectrum set basically is the set of all genus greater than or equal to 2 so that it acts on sigma g. Okay, so this question is kind of named as a Hurwitz problem. So I guess this is due to, I should write it over here. This is probably due to Miller and Maculo. Okay, so it's probably around 1990s or sometime. So they were looking at one of the theorem I'm going to just state after this. So this is these cofinite theorems by Ravi Kulkarni around 1987. So Miller and Maculo just tried to mimic the same process, but when the group acts and the quotient become a orbifold, so they got something very similar result, but it's a different type of calculation. Okay, so this question, if you just now, whatever I asked this, if I try to compute this set for various kinds of finite groups, this is known as Hurwitz problem. And this gets a bit simpler if I just look at this cofinite theorem. So this is what I was mentioning in the beginning. So for a finite group, there is always a number, positive integer, which is kind of computable from the structure of the group, so that my group would act on a genus means the genus has to be congruent to 1 modulo this number. And except for finitely many G's congruent to 1 modulo n, the remaining ones would always act. Okay, so that basically tells you that if I looked at the arithmetic set, so set of all integers of the form 1 plus capital N times lambda, where lambda runs over all possible positive integers, probably you would like to take not over here. No, okay, fine. So from this, if I just try to subtract the spectra set, so this is finite. So this says that there are at most finitely many points over here, which probably would not be the genus for this particular group, capital G. So this means I would be focusing on 3 things. So first of all, one would be the minimum genus, which is I would like to compute what is the minimum of the spectra set. I'd like to compute some number which is called stable upper genus. So this is basically because all the spectra elements are now some kind of arithmetic part of this arithmetic set. So you look for the sigma, which is the one beyond which all elements of this arithmetic set are also genus of this group. So for every G congruent to 1 mod n, which is beyond the sigma, turn out to be a spectra. Okay, so these 2 are 2 of the main ingredients, and then I need to look forward to, so what are the integers in between this, which are in the arithmetic set, but not in the spectra. So this is usually named as the spectral gap sequence. So one of the important immediate consequence of this is if I find out 2 groups which for which my mu G and sigma G are exactly equal, then for this, the spectra would be the same. And this is where really the focus lies, that you don't try to compute bluntly, just pick up group and try to compute the spectra set. You would like to find out what could be the group theoretic invariants or properties they share so that the spectra sets are exactly turn out to be the same. So this is a discovery which is kind of more challenging, and I'll tell you some answers soon. Okay, so because of the scale version, so one can also look at the scale version of these invariants. So for instance, I will call SP naught the set of all lambdas, so that precisely 1 plus lambda times n times lambda times ng would be in the spectra. So it's basically the set was something like this, and then you subtract 1 from the genus and divide by n. It looks much simpler to you now. So this is the scale spectra. And similarly, this mu and sigma, you can also scale them by subtracting 1 and divide by this capital N of G. So this is the scaled minimum genus, scaled stable upper genus. Okay, so let's try to focus on the 3 directions right now as what I'm going to talk about. So first one is a counterexample to this Talu's abelian P group conjecture, so which is kind of settled around 2019. It was published. And the second one is, which is yet to come up, something called uniformity in finite P groups. And I'll discuss some experiments in the past which is done on non-P groups. Some of these myself and the other authors. So what is Talu's abelian group conjecture? So in short, I'll just write it as a tag, so which is no more true. So it basically states as follows, that can we recover the structure of an abelian P group? So P group means its order is a power of a fixed prime. So the question is, can you recover the structure of the finite P group, which is abelian, determined by the spectra sets? So of course, if the groups are isomorphic, then the spectra sets are the same. But the question is the converse also true? So the reason, there were some definite reason that this actual conjecture was actually coming up, and we almost expected to hold. So here is the reasons. Let me just explain. So if we just have an abelian P group, let us write it down in the form of this primary decomposition, and I'll write it a little differently. Instead of putting powers of P over here, I'll just try to find out copies of Z mod PZ, the cyclic group of order P. So there are, let's say there are R1 many copies of this, R2 many copies of Z mod P square, and so on. So the exponent of this group is actually Z mod. So this is the P power E is the exponent. And it might happen, of course, that some of the Ri's are 0. And this one, RE has to be at least 1. Otherwise, I would just knock it off. Okay, so the Talu's abelian group conjecture actually turn out to be true in certain cases. So for example, first one, these are the listed as follows. The first one was the cyclic P groups, where I have some exception, but exceptions usually are not counted when you try to generalize something. So this was due to Kulkarni and Maclachlan. I think this was around 1992 or something. And the second evidence of this was abelian P groups of rank 2. So by the word rank, I mean how many pieces of cyclic groups that are there in this decomposition. For example, this one rank is the sum of these powers over there. Okay. So in case there rank 2 abelian P groups, with an exception again of this 2, Z2 cross Z4 and Z2 cross Z8. The remaining ones actually all satisfy these rank 2, the abelian P group conjecture. So if you have 2 finite P groups which are of rank 2, and other than this 2, then the spectra actually determined up to isomorphism these groups. The third one was elementary abelian P groups. This is again another exception of Z2 and Z2 cross Z2. So again, let me just mention these works. So this second one was due to again Talu. And this one was Maclachlan and Talu. Okay, I don't remember the years of these papers were published. The second one, Maclachlan and Talu, was Yasmin Talu's PhD thesis, where elementary abelian P groups were discussed. And she went ahead with computing the rank 2 case and also this abelian P group of exponent P square case. So these two facts appeared something in the Journal of Korean Math. Okay, so I don't remember the exact details, but this is exactly the place where people started suspecting that probably this is a conjecture. So you get very high rank, but stick to that exponent being P square, then without any exception, these conjectures start looking to be true. Okay, so now let me try to explain where the counterexamples and how they actually came from. So there is something called finite P groups of Gorenstein-Kulkarni type. So I'll be not talking about this until probably the end. So these groups I was trying to experiment on, and then I found out among the abelian P groups which are of this type, they are some of these kind of showing some kind of counterexample to what Talu was expecting. And obviously that has to be of beyond exponent P squares. So I found out that they were exponent PQ. So let me just formally explain what it was. So suppose you have an invariant form of this. So you write down again the group to be the direct product of primary decomposed components. And these invariants, so these are not actually in the previous form. So these invariants, I would call it large. If my E is at least 2, the invariants until the last one, so except the last one, they all are at least p minus 1. And the last one is greater than equal to p minus 2 or 1. So this was kind of written down to, so for p odd, this is greater than equal to p minus 2. That should be the case. But this is kind of kept to make sure that in case p equal to 2 also this should work. So in that case, RE is any arbitrary positive integer should work. So I would call the group as large invariant. With group is with large invariant if such thing happen. And this was the result, that if you take a finite abelian P group with large invariants, then the scale spectra actually coincide by showing up their minimum genus and the stable upper genus are exactly the same. So here this theorem says that the scaled minimum genus and the scaled stable upper genus coincide with this particular number. And once this happens, their scaled versions of the minimum and stable are also the same. And there is no difference between the spectra set. So if one expect to find out a counterexample, the idea should be find out two abelian P groups with different invariants, which are both large. However, this particular quantity for both of them has to be the same. Both of them should have the same order and same exponent. Okay, so for example, let's take this one.
When did the paper appear?
So this appeared in Glasgow Math in 2009. So this paper is actually full of infinite type of counter examples. So I mean, with varied exponents and varied orders and so on. So I'll just give a glimpse of what the kind of counter examples you can immediately look forward to. So let's look at this group G1, which is the first invariant type is P minus 1, then second one is 3P, third one is P minus 2. And now remember that largeness definition was there. So all these actually satisfy this largeness. And the second one I would take to be this one with these invariants over here. First one is 2P plus 1, second one is P minus 1, and third one is 2P. So again, from my definition of largeness, both of these are satisfied. And here I have to be slightly cautious. I'm taking P to be odd. Obviously, otherwise this would be 0. And then there'd be a problem. Okay, so then both of the case, you can just actually see that they have the same order, which is P power 10P minus 1. And if you try to compute this invariance over here, they turn out to be equal. So their scale minimum spectra and scale stable upper spectra are exactly coinciding. So their spectra sets are exactly the same. But obviously, if you look at carefully, the invariants I have put up on top of this, for obvious reasons, they cannot be isomorphic. So the reason, I mean, I won't give a proof, but some kind of idea of why it happened is that you try to look forward to something like this and try to find out fixing a P. How can you solve this equation with fixing some kind of with respect to Ri? So fix your P, fix your E over here, and this I runs from 1 to E. Again, all these coefficients are kind of fixed. Then you try to solve these for Ri with a constant. And the minimum counter example, the smallest order counter example for P odd, what you would be finding out is this one. So that was the reason why we had to put a P minus 2, which is kind of below which it's nearly impossible to go. And if it goes, then again, Talu's conjecture turn out to be true. Okay, so Once this was settled, now one of the questions should be that whenever this counterexample happens, can we kind of formally write it down? And these are kind of large invariants. So for non-large invariants, if there are some low order invariants that come in between somewhere, can we kind of finding out the spectra coincidence? So this is kind of very difficult. It kind of looks, and I would rather say this large invariant is one lucky case somehow where it was settled. Okay, so I'll go to the next topic. So this is called uniformities in finite P groups. And again, the kind of motive was to find out lots of groups which are with respect of fixed prime P, which are all finite P groups. But there is some kind of coincidence among the spectra sets. So let's say they have at most finitely many spectra sets. So let's formally try to write it down as follows. You have a fixed P and you write a property among these finite P groups with respect to a fixed prime. Of course, I don't want to make it explicit. The speed does not usually should depend on little p. Okay, so for example, I can say p being cyclic, so it doesn't depend on your what little p you are taking. Okay, and then I would look forward to for a fixed integer n and some e in between 1 and n. Look forward to all possible finite p groups whose order is p power n and exponent is p power e, and they would satisfy this property p. Okay, and now I would say that this property p is uniformly symmetric if this number of spectra sets among these groups which come from these which satisfy these properties, which have this fixed p power n order, fixed p power e exponent, and they satisfy this property p, they should be bounded above by some number d, and I expect that d to be independent of these three elements. Okay, so obviously, I mean, if I don't want this is independency, the statement is obvious, because you see that the number of groups which lies over here is finitely many always. These are basically the groups of order at max p power n. Actually, I'm looking at group exactly of order p power n. So there are finitely many such groups. Okay, so what it says is that I should be putting in uniform bound over there, so to speak. There is a uniform geometry that is happening on towards this group. Okay, so for example, a trivial example, you can again look forward to that p being a cyclic group. So then my order is p power n, so I'm putting a n over here. This one is exponent, so a cyclic group has exponent p power n again. But this set actually has a single group inside it, and the spectra set should be just containing one spectra. Okay, so this is obviously not a reason why one can expect that this uniform symmetry, and the reason behind why such definition we want to pose. So before I go to the next result, let's just brush up through some definitions. So for a finite P group, they are always nilpotent. This is again a standard fact. And if I look at the nilpotency class to be just written down and like class G, or sometimes I'll denote it by little c, then the co-class is called the log base P order of that subtracted by this class of G. So that is to speak, if I just have the group has order P power n and nilpotency class C, then co-class is simply n minus c. And for obvious reason, nilpotency class cannot exceed n, and in fact c is always less than equal to n minus 1. So this is again a standard fact. So okay, and the question is now, is it possible to find out examples of C being equal to n minus 1? And the answer is yes. So these groups are usually called maximal class. And for every n greater than equal to 3, there exists a P group, finite P group of maximal class of order P power n. Okay, so this is again standard fact. And these groups are quite a few. Okay, so for example, you can just look at for P equal to 2, there are the 3 groups which are called, first one is called generalized dihedral group and generalized quaternion. And the third one is semi-dihedral. So the way to describe this is that this relations just tells you that you are basically looking at what cyclic group generated by X and cyclic group generated by Y. And then this one just explains that this is basically a semi-direct product of cyclic group generated by one with respect to the other one. So the cyclic group generated by X become a normal subgroup, and this is a semi-direct product. The third one, the semi-dihedral also is a similar case because the relations looks very similar because these two are generating cyclic groups over there, and you have a semi-direct factor given by some kind of unit in the ring modulo 2 power n. Okay, so the quaternion stays a bit away from this. This is not a semi-direct product, but this is rather an amalgam of two cyclic groups. When you look at a group of dihedral type of order 2 power n plus 1 and then amalgam certain subgroups, and then you end up getting this group. Okay, so these 3 are examples of finite two groups of maximal class. And there is a theorem which says that any 2 group of maximal class should be one of these 3. Okay, so that tells you there are again pretty much 3 distinct types of these groups. And even if I try to pose a question like for P equal to 2, I look at the property of P being of property of co-class 1, then there are 3 possible types and I won't get anything out of it. The spectra set there will be at most 3 spectra because there are at most 3 different groups. However, for P odd, there are examples. For example, if you take any non-abelian group of order P cube, that turns out to be maximal class for obvious reasons. Any abelian group of order P square, that should also be treated as maximal class. But the most interesting part of P groups of maximal class actually starts beyond the order P power 4. So if you look at the groups of co-class C and order P power n, let's take co-class 1 C equal to 1 over here, then number of such groups actually goes to infinity as your order grows. So this is kind of comes from a very estimate. There is no classification, of course, but kind of estimating the numerical growth property, that number of P groups of fixed co-class diverges to infinity along the order beyond P equal to 3. Okay, so here is the result I'm going to quote now, which should be evident to show that, okay, the co-class property or co-class 1 property is one of the uniformity properties. So if you look at all the spectra sets of co-class 1 with a fixed order n and e, then it is always bounded over by 6. So this is our recent work, and it's going to appear in Journal of Algebra and Applications. So beyond this, one should look forward to a conjecture like this, that this co-class property, whether it's uniformly symmetric, and that would basically settle the entire the Hurwitz problem for finite P groups. I will end it up with a few examples on the last experiments. So this co-class, the spectra sets are computed for kind of quite a few sporadic classes of groups. Of course, we were not been able to experiment on Lie types because the order suddenly become very high. There are too many element orders, and then it become very difficult to experiment on those. Then groups of order PQ, this work is done by Weaver. When this is a non-abelian group, actually this is it actually happens when the P is a prime which is distinct from Q, and P divides Q minus 1. So in those cases, such groups occur. And Tony Weaver actually classified the spectra sets for those. But one of the bigger challenge was the cyclic groups of non-prime orders. So for order PQ, there is a very long paper by O'Sullivan and Weaver describing the spectra sets. And it would be really nice to see if somebody can go beyond this, which is, well, PQ is already quite a complicated answer. So I would not know. Yeah, so beyond this, I would probably stop here. And beyond this, if there are questions, I would like to answer.
Okay. Okay. So let's thank the speaker. Yeah. Yeah. Is there any question from the audience?
Up to P power 8 is kind of, I won't say classified only, but it's also in the gap.
No, I think they're actually classified.
There is no paper, but it's some kind of project work by O'Brien and other students.
It's not.
This list is not available, but it's secretly available. No, it's actually classified. P-power 7, P-power 4, but it's not available in literature. So there are algorithms, actually those are made using these numeric parameters. So at one point I remember I found out a 2008 article of O'Brien and one of the students, which is written down each and every stages of how the algorithm should work. So this is probably a public information, but not published as a paper because it's 2000 page, nobody will accept.
2000 page.
Yeah. So somebody asked O'Brien, Yemen, that you like to go for P-power 9 now? He said, he's forgetting. Someone else can be.
Half of them are yeah, that's the extreme case. We're just talking about the big group. So isoplanism.
That's the standard technique. I mean, one of the parameters is isoplanism. So you want to.
So how about the spectrum problem and isoplanism?
A priori, the answer is no. But what we have seen is that there is these Gorenstein-Kulkarni type groups where these are automatically isoclinic if you just take some kind of central extensions. And then there's spectra sets also one can just try to look at. I mean, I won't say these are exactly the same, but there is some kind of similarity. Still, in the general case, it's on the conjecture level, so I won't be able to say anything about that.
Isoplanism, isoclinic, this is a very.
See, what isoclinic does is
Philip Hall. Genius of Philip Hall.
it's modulo center and the
many variants are same.
so commutator and center, modulo center, that the pattern how it looks like. But sometimes that doesn't give you a very good advantage when you try to look at compute the spectra.
Okay, so any more comments?
Yeah, in some ways the infinite cases are easier than the finite cases. This is the general mathematical philosophy.
Okay, so let's thank the speaker again. We will resume at 2:30.
Battery getting. Oh.